Real numbers all have a purpose. Whether you're planning holiday costs or analysing a sports game, it's clear why we need real numbers. But what about complex numbers? How can the square root of -1 actually be used in the real world? By the title of the video, you can probably guess it's for sound. But before we can do that, we need to visualise complex numbers with a 2D plane. We'll have real numbers on the horizontal axis and imaginary numbers on the vertical axis. This complex plane or Argand diagram is how we'll show complex numbers. All complex numbers can be written in the form a plus bi, where a and b are both real numbers. So we can put any complex number on this graph by going along the real axis to a and up the imaginary axis to bi. So if we go right to 1 and up to I, we get the number 1 plus I. And similarly, if we go -3 to the left and 4i up, we get the number -3 plus 4i. We can add and subtract numbers by looking at their individual components. So -3 plus 4i minus 1 plus I would give -3 minus 1 plus 4 minus 1i, or -4 plus 3i, which would be here on our Argand diagram. With multiplication, we can just expand the brackets. So with our numbers from before, we get -3 plus 4i minus 3i plus 4i squared, which becomes -7 plus I, as I squared is just -1. We can also look to multiply complex numbers graphically. If we look at the angles our original numbers make with the real axis, and add the angles together, we have the angle the product makes with the real axis. We can compute the magnitude of each point using Pythagoras. So the magnitude of 1 plus I is the square root of 2. The magnitude of -3 plus 4i is 5, and the magnitude of -7 plus I is the square root of 50, or 5 root 2. When we look at the magnitudes of each line, we find that we have just multiplied the first two magnitudes to get the last magnitude. In fact, any complex multiplication can be found by adding angles and multiplying magnitudes. Here are the rigorous proofs, but don't worry if you don't understand them, as they are not the focus of this video. They're just here for completeness. Now we know how complex numbers change under multiplication, we can look at the Euler representation of complex numbers, re to the I theta, where r is the magnitude of the number, and theta is the anticlockwise angle in radians from the real axis, also known as the argument. We're going to show how we get here by using something called a Taylor expansion, which gives us a polynomial expression of a function based on a known value and the function's derivatives. Each term in the polynomial can be written as Cn multiplied by x to the n, where Cn is just a constant term. Let's see how we can get e to the x in this form. We need a polynomial whose derivative is itself, as the derivative of e to the x is e to the x, and whose value at x equals 0 is 1, as e to the 0 is 1. If we sub in x equals 0 to both sides of the equation, we end up with 1 equals c0, which we can sub back in. If we differentiate both sides of the equation, we get e to the x equals c1x0 plus 2c2x to the 1 plus 3c3x squared, and so on, with the nth term becoming ncn times x to the n minus 1. We can equate coefficients to find the remaining constant terms. So c1 equals 1 from the x to the 0 term, 2c2 is equal to 1 from the x to the 1 term, so c2 is equal to a half. Looking at the x squared term, we get 3c3 equals a half, so c3 is equal to 1 over 6. If we look at the x to the n minus 1 term, we find that ncn is equal to cn minus 1, so cn is equal to 1 over n, cn minus 1. If we now sub n minus 1 into n in this expression, we get cn minus 1 equals 1 over n minus 1, cn minus 2. So subbing cn minus 1 back into the cn expression gives 1 over n minus 1, cn minus 2. We can continue subbing constants until c1, giving Cn equals 1 over n factorial times C1. But C1 is equal to 1, so Cn is equal to 1 over n factorial in general. So we can write e to the x as an infinite polynomial sum as follows. In essence, this is an induction proof, as we have found the nth term in the sequence from previous terms, and we have found the first term of the sequence. Let's now consider sine and cosine as well. We'll write an for the nth term in the cosine polynomial, and bn for the nth term in the sine polynomial. The derivative of cosine is minus sine, and cosine of 0 is 1. The derivative of sine is cosine, and sine of 0 is 0. When we sub x equals 0 to both equations, we get a0 equals 1 and b0 equals 0, so we can put 1 and 0 as our constant terms. We can rearrange the derivative of cosine so that minus the derivative of cosine is sine. Differentiating both sides of the cosine equation and multiplying by minus 1, we get a new equation for sine. Similarly, we can differentiate both sides of the sine equation to get a new cosine equation. If we equate terms as we did before, we can find all of these constant terms. From the x to the 0 term in the sine expansion, a1 is 0, and the cosine expansion gives b1 is 1. Looking at the x to the 1 in sine gives a2 equals minus a half, and from the cosine expansion, b2 equals 0. The a3 term is 0, and the b3 term is minus 1 over 6. We'll now consider the case where n is even and look to find the nth term of the cosine expansion and the n-1th term of the sine expansion, as the odd terms of the cosine expansion and the even terms of the sine expansion are always 0. For the cosine expansion, we see that the nth coefficient is minus 1 to the power of n over 2 divided by n factorial, and for sine, the n-1th coefficient is minus 1 to the power of n minus 2 over 2 divided by n minus 1 factorial. Try to see if you can prove this yourself. If you look online or in a textbook, they'll often have the nth term of both equations written like this, as usually the 0 terms aren't considered. Let's look at the three Taylor series together. If we replace x with ix in the e expansion, we get an expression that simplifies to 1 plus ix minus a half x squared minus I times 1 over 6 times x cubed, and so on, with the nth term being 1 over n factorial multiplied by ix to the power of n. If we multiply our sine expansion by I, and then add our cosine and I sine expansions, we get the following sum. Comment down below if you can figure out why the nth term is 1 over n factorial times by ix to the power of n in the sum. If you're watching this after the 29th, there will be an answer in the description of the video. Comparing expansions, we find that cosine of x plus I sine of x gives e to the ix, and we have Euler's formula. Well, one of them. If we consider where our complex number appears on the Argand diagram, we can draw a line from the origin to the point with magnitude r. We can draw on the argument theta and find that the real and imaginary parts can be written as r cosine theta and ir sine theta respectively. We can factor out the r from our expression to get r cosine theta plus I sine theta, but Euler's identity tells us that this is just r e to the I theta, and therefore we have our Euler representation. It's important to remember that we use radians rather than degrees when using this form. If we use degrees, the derivative of sine x would be cosine of x, the derivative of cosine would be minus sine of x, and therefore Euler's formula wouldn't hold. If you're interested as to why the derivatives change, there is a black pen red pen video linked in the description which fully explains this idea. Now how does this apply to sound? Let's look at a sound wave. We can represent it with a curve as follows, where the horizontal axis is time and the vertical axis is the size of the wave, or the amplitude. If this shape looks familiar, it's because this is just the sine function, where f is the frequency or number of full oscillations per second, and t is the time passed. Increasing the frequency increases the number of oscillations per second, and we get a higher pitch. Increasing the magnitude of the function increases the amplitude of the wave, and we get a louder sound. By adding multiple sine functions with different frequencies, we can get different harmonies, and this is the basis for all sound. This curve only applies over 0.02 seconds. For a 1 second time period, the graph looks more like this. As cosine just shifts the sine graph, replacing sines with cosines translates the wave pi over 2 seconds left. In fact, this general process of adding sines and cosines, or e to the I thetas, gives us something called a Fourier series, which is a very useful tool when working with waves. In general, we use the complex form more often than the trigonometric form. But why is this the preferred method? Well, the rules of algebra still apply to the Euler representation, and calculus is far nicer with exponential terms than trigonometric terms. This allows us to use techniques you might see at a university level, such as Fourier transforms, so it's generally better for a computer to work with the Euler representation. Of course, both representations are useful in different scenarios, and engineers, physicists, and mathematicians often choose which form to use based on which one makes their specific problem easier to solve. However, the fact that imaginary numbers are being used to make the real sound coming through your device is frankly incredible. Wait, before you go, I am making this video as a part of my university course and need to collect feedback. I have to give a written evaluation on the quality of the maths communication, so I would seriously appreciate it if you could fill out the feedback form in the description. Any criticisms or compliments are more than welcome. Thanks for watching.